Have you ever stopped for a moment and asked yourself a simple question? What exactly is time? You check your watch, you remember yesterday, and everything seems clear. Time feels like the most natural thing in the world, but the way you experience time inside your mind is not the same thing as time itself. Most people imagine time like a river, carrying us from the past to the future. It's a poetic idea, but it hides a serious problem. In physics, time does not move like water. The sense that time is passing is actually something your brain constructs. It is a sensation created by biological processes inside your head, a messy system built from clever mental tricks. To understand time, we have to look past our intuition. Stay tuned as we explore the fascinating ideas behind science and our universe. And here's where it becomes interesting. A person who uses that visual system can sometimes continue counting even while doing something else, like reading a sentence or checking a list. Their brain is running two different processes at once, one visual and one verbal. Meanwhile, the person who counts using an internal voice cannot read and count at the same time without losing track. The two tasks interfere with each other because they rely on the same mental machinery. What does this tell us? It shows that the way you experience time is not universal. Your brain constructs its own internal method for tracking duration, and that method varies from person to person. What feels like the steady passage of time is actually your mind recognizing patterns in sequences of events. It is a mental process, not a fundamental property of the universe itself. This is why physics cannot rely on human feelings when it talks about time. If scientists tried to define time based on how it feels to us, the definition would change from person to person. Instead, physics uses a very different approach. It focuses on measurement. In science, time is not treated as a mysterious flowing substance. It is simply a way to organize events. Think of it like placing playing cards in a row on a table. One card comes before another, and another comes after. The order exists because of how the cards are arranged, not because the table itself is moving. In the same way, time is the structure that allows us to say one event happened before another. It is a labeling system that helps us describe the sequence of changes happening in the universe. This idea leads to an important realization that challenges our intuition. Many people imagine time as a background stage where everything happens. They think of the universe as a giant empty box with time ticking away like a clock on the wall. In that picture, even if all the stars disappeared and all the atoms vanished, time would continue ticking. Second after second would pass in an empty universe. But modern physics tells us that this picture is wrong. Time is not a stage on which the universe performs. Time is part of the performance itself. It is a way of measuring change within the universe. If absolutely nothing changed, no atoms moving, no light traveling, no energy shifting, then time would lose its meaning completely. Without change, there would be nothing to measure. Every clock we use relies on some physical process, a pendulum swinging back and forth, a quartz crystal vibrating, or atoms oscillating inside an atomic clock. These processes provide the rhythm that allows us to mark seconds. Without those physical changes, the concept of time would simply disappear. Now think carefully about what that means. If every clock in existence relies on some kind of physical change, a pendulum swinging, a crystal vibrating, or atoms oscillating, then time cannot exist independently of those changes. Time is not a thing floating around the universe like an invisible current. It is simply the way we keep track of transformations happening in the physical world. This idea is very different from the one most people carry in their heads. Many of us imagine time as something that acts on objects. We say things like, "Time makes us older," or "Time spoiled the milk." But that language quietly hides a mistake. Time does not cause anything to happen. Time is not an active force. Milk turns sour because bacteria multiply and chemical reactions take place. Your body ages because cells divide. DNA accumulates damage and biological processes gradually change your tissues. None of that is caused by time itself. Those events happen because of physical processes interacting with each other. Time is simply the ruler we use to measure how fast those processes occur. Imagine building a house. You measure boards with inches or centimeters. But inches did not build the house. Carpenters did. The measurements simply help describe the structure. Time works the same way. It does not perform the work of the universe. It records the order and rate at which things happen. Once you begin thinking about time as a ruler rather than a flowing river, another strange question appears. What if that ruler is not perfectly rigid? For centuries, scientists believed that time was universal. If two clocks existed anywhere in the universe, they should tick at exactly the same rate. A second on Earth would be the same as a second on Mars, on Jupiter, or anywhere else. That assumption felt obvious. It matched everyday experience. But modern physics has shown that it is completely wrong. The rate at which time passes depends on two things: how fast you are moving and how strong gravity is around you. This idea is at the heart of Einstein's theory of relativity. To understand it, imagine you are driving a car across a huge flat sheet of paper. You can drive north or you can drive east. If you drive directly north, all of your motion is going in that single direction. But if you turn the steering wheel and head northeast, your motion splits between the two directions. You are still moving, but you are not progressing north as quickly as before because some of your motion has been redirected east. Now replace the directions in that picture. Instead of north and east, imagine the directions are time and space. According to relativity, everything in the universe is constantly moving through a combination of space and time. The total amount of motion is fixed, but it can be distributed differently depending on how you move. If you sit completely still in your chair, almost all of your motion is directed through time. You move forward through time at the maximum rate possible. But the moment you start walking, driving, or flying in a rocket, some of that motion shifts into space. Because your motion is now divided between space and time, your movement through time slows down slightly. Your clock ticks more slowly. This effect is not a malfunction of the clock. It is a real feature of the universe itself. Time literally passes at different rates for observers moving at different speeds. At ordinary human speeds, the difference is extremely small. When you run for a bus, your watch slows down by such a tiny amount that you would never notice it. But the effect becomes significant when objects move very fast. For example, satellites orbiting Earth travel thousands of kilometers per hour. Because of that speed, time for the clocks on board those satellites runs slightly slower than time for clocks on the ground. At the same time, gravity also affects time. Strong gravitational fields slow down the passage of time compared to weaker ones. GPS satellites experience both effects at once. Their clocks run differently from clocks on Earth because they are moving quickly and because they are farther away from Earth's gravitational pull. Engineers must correct for these differences using Einstein's equations. If they didn't, the timing errors would quickly accumulate, and your GPS location would drift by kilometers within a single day. So the strange conclusion is unavoidable. Time is not the same everywhere. It stretches and compresses depending on motion and gravity. What feels like a steady universal clock is actually something flexible, something woven into the structure of space itself. Once you accept that time can stretch and compress depending on motion and gravity, another puzzle begins to appear. Even if time behaves differently in different places, we still feel that it has a direction. We feel that time moves from the past toward the future. Yesterday is fixed, tomorrow is uncertain. We remember what has already happened, but we cannot remember events that have not occurred yet. That sense of direction seems obvious, almost unavoidable. But here's the strange part. Most of the fundamental laws of physics do not actually care about the direction of time. If you take many physical equations and replace time moving forward with time moving backward, the equations still work perfectly. Gravity still works. Electromagnetism still works. A planet orbiting a star would follow the same path whether the film of its motion is played forward or backward. Imagine recording a video of a planet moving around the sun. If you reverse the footage, the motion still looks natural. Nothing in the laws of physics seems to forbid that reversed sequence. Now compare that with something from everyday life. Imagine filming an egg falling from a table and smashing on the floor. When you watch the footage normally, it looks completely ordinary. But if you reverse the video, something feels deeply wrong. The broken pieces of shell suddenly leap off the floor, the liquid yolk pulls itself together, and the egg perfectly reassembles in midair before landing back on the table. Everyone immediately recognizes that the reversed scene is impossible in real life. So if the basic equations of physics often allow both directions of time, why does our everyday experience seem to favor only one direction? Why do we only see eggs breaking and never see them spontaneously rebuilding themselves? The answer lies in a concept called entropy. Entropy is a measure of disorder or randomness in a system. A highly ordered system has low entropy, while a messy or disorganized system has high entropy. Consider the egg again. A whole egg sitting on a table is a very specific arrangement of matter. The shell, the yolk, and the white are all organized in a particular structure. There are very few ways for that arrangement to exist. But once the egg breaks, the number of possible arrangements becomes enormous. The shell fragments can scatter in countless directions. The liquid contents can spread across the floor in almost infinite patterns. That means the broken state is far more probable than the intact state. Whenever objects interact and energy moves around, systems tend to evolve from less probable arrangements to more probable ones. Order gradually gives way to disorder because there are simply more ways for things to be disordered than to be perfectly organized. This statistical tendency creates what we call the arrow of time. The arrow of time is not a force pushing events forward. It is simply the direction in which entropy increases. When you watch an egg fall and break, you are seeing the universe move from a highly ordered configuration to a more disordered one. That transition is extremely likely. The reverse process, millions of particles spontaneously rearranging themselves into a perfectly structured egg, is so unlikely that it effectively never happens. This is why your brain can remember the past, but not the future. Memories themselves require physical records. Your brain stores information by forming patterns in networks of neurons. Those patterns are created through physical processes that increase entropy. The act of forming a memory is itself part of the same one-way progression toward greater disorder. Because of this, the past leaves traces behind while the future does not. Your brain contains records of earlier states of the world, but it has no physical records of states that have not yet occurred. That asymmetry creates the feeling that time flows in one direction. In reality, what you are experiencing is the universe gradually moving from states of lower entropy to states of higher entropy. You can think of it like shuffling a deck of cards. Imagine you start with a perfectly ordered deck. With each shuffle, the arrangement becomes more mixed. After enough shuffling, the deck reaches a state where no recognizable order remains. You could keep shuffling forever, but you would almost never return to the original perfectly ordered arrangement. The universe behaves in a similar way. Over time, systems tend to move towards states that can exist in more possible configurations. Those states appear more random and less structured. Your sense of time moving forward is really your brain noticing that change. You are not detecting time itself. You are detecting the increasing disorder of the universe around you. And once you realize that your sense of time's direction comes from entropy, something even more unsettling begins to appear. The thing we casually call now, the present moment that feels so immediate and real, is not as universal as we tend to imagine. In everyday life, we assume that everyone shares the same present. If two people stand next to each other, they both agree on what moment it is. But the moment you move away from that everyday scale and begin looking at the universe through the lens of relativity, the idea of a single universal now starts to dissolve. To understand why, imagine two observers far apart in space. Suppose one person is standing on Earth and another is on a planet 1,000,000 light years away. If both of them remain at rest relative to each other, their definitions of now will line up fairly closely. Events that one considers to be happening at this moment will also be considered present by the other once the travel time of light is accounted for. But the situation changes the instant motion enters the picture. If that distant observer begins moving rapidly away from Earth, relativity tells us that their sense of what counts as now tilts relative to ours. Events that we consider to belong to our present might lie in that observer's past or future. Their slice through the timeline of the universe cuts through events at a different angle. In other words, there is no single universal moment that stretches across the entire cosmos like a blanket covering everything simultaneously. Physicists often describe the universe not as a sequence of moments, but as a four-dimensional structure. Imagine a loaf of bread where each slice represents what someone might call a now. Different observers moving at different speeds cut that loaf at different angles. The loaf itself, the full collection of events across space and time, remains the same, but each observer divides it differently depending on their motion. This idea feels deeply counterintuitive because our everyday experiences never expose us to situations where the differences become noticeable. The speeds we move at in daily life are tiny compared with the speed of light. At those speeds, the differences are essentially invisible. Our brains grow comfortable with the illusion that there is one universal present, but at cosmic distances, the illusion breaks down. Our minds evolved to solve practical problems in a narrow environment. For generations, we lived where distances were short and speeds were slow. Those shortcuts became what we call common sense. But when we apply them to cosmic scales, they often lead us astray. In reality, time is woven together with space into a single structure called space-time. Gravity bends this geometry itself. For everyday purposes, time behaves like a steady clock, but underneath, the universe is far more subtle and flexible than we ever imagined. If time is really a way of measuring change within the universe, then the most natural question we can ask is what happens when we rewind all those changes back to the very beginning? Imagine running the entire cosmic film in reverse. Galaxies that are currently drifting apart would slowly move closer together. The distances between clusters of stars would shrink. The universe would become denser and hotter as everything collapsed back toward its origin. Keep running that film backward far enough and you eventually reach a moment when the universe was unimaginably small, dense, and energetic. This moment is what physicists refer to as the Big Bang. But here's where our everyday intuition about time begins to struggle again. If the universe had a beginning, we naturally want to ask what happened before it. We want to imagine a timeline stretching backward into some earlier era, a kind of cosmic preface to the story of the universe. It feels impossible to accept that the timeline might simply start. Yet our modern understanding of physics suggests that this instinct may be misleading. Remember the definition we developed earlier. Time is not an independent river flowing outside the universe. Time is a way of ordering events that occur within the universe. If that definition is correct, then the beginning of the universe might also mark the beginning of time itself. In other words, asking what happened before the Big Bang may be like asking what lies north of the North Pole. At first glance, the question sounds perfectly reasonable. Grammatically, it is well formed, but geographically it makes no sense. The North Pole is already the northernmost point on Earth. There is no location further north than that. If time truly began with the universe, then there may be no earlier moment for the timeline to extend into. The sequence of events simply starts there. This idea creates a strange tension between physics and human psychology. Our minds are built to expect continuous stories. Every event in our daily experience has a cause that came before it. A falling object was dropped, a building was constructed, a conversation began with someone speaking the first word. Because of this pattern, we feel uncomfortable with the possibility that the universe itself might not have a previous chapter. But physics often forces us to confront situations where our instincts fail. The early universe was so dense and energetic that the laws of physics, as we currently understand them, begin to break down when we try to describe the very first instant. Our equations work extremely well when we look back to a fraction of a second after the Big Bang. But as we approach the exact beginning, the mathematics becomes uncertain. This does not mean that the beginning is unknowable forever. Scientists continue searching for deeper theories that might describe those earliest moments more clearly. Some proposals suggest that our universe may have emerged from quantum processes. Others explore the possibility that what we call the Big Bang was actually a transition from an earlier state of reality. Time cannot be separated from the physical universe. Any explanation of the beginning must account for time being part of the system. This brings us back to mental models. When you count seconds, do you hear numbers or see a visual scale? While both track duration, the internal mechanisms differ. This reveals how our minds translate abstract concepts. Older theories treated time as a steady ticking clock, a simple background to reality. But Einstein's relativity revealed space and time are linked, stretching and compressing with gravity and motion. What once seemed like a simple backdrop has turned out to be a dynamic, flexible part of the universe itself. We think we share the same picture when we talk about the cosmos, but this reveals an unsettling truth. Even when we agree on the science, each mind translates words into its own entirely unique and private mental imagery. You might hear the phrase 1 minute and picture a digital clock counting down. Someone else might imagine the ticking of a mechanical watch. Another person might visualize a line of numbers extending forward. All of those internal images lead to the same conclusion, but the experience behind them is unique to each individual. This is one of the reasons scientific ideas often feel difficult to communicate. Words are shared, but the mental pictures behind those words can vary dramatically from person to person. In everyday life, this difference rarely matters. If two people agree to meet for coffee at 2 o'clock, their watches will guide them to the same moment regardless of how they internally imagine time. But when we try to understand something as abstract as space-time or the structure of the universe, those internal pictures suddenly become important. The mental image you use can either help you understand the concept or quietly block you from seeing it clearly. If your mind insists on picturing time as a rigid tape moving steadily forward, then ideas like time stretching, slowing down, or depending on motion will feel impossible. But if you replace that picture with the idea of time as part of a flexible, four-dimensional structure, the strange predictions of relativity begin to make sense. This process is similar to upgrading software in a computer. The hardware, the human brain, remains the same, but the conceptual programs running inside it can be improved over time. Science advances by rewriting those programs. Centuries ago, people believed the Earth was the center of the universe. Later, we learned that Earth is simply one planet orbiting a star. Even later, we discovered that our star is just one among hundreds of billions in a galaxy, and that our galaxy is only one among trillions. Each discovery forced humanity to replace an old mental model with a new one. Our understanding of time has gone through the same transformation. What once seemed like a universal ticking clock has turned out to be something far more complex, a dimension intertwined with space, influenced by motion, gravity, and the structure of the universe itself. And yet, despite how strange this deeper picture becomes, our everyday experience of time continues to function perfectly well. You can still set an alarm, cook dinner for 10 minutes, or meet a friend tomorrow afternoon. The extraordinary behavior of space-time hides beneath the surface, invisible to our daily lives. But knowing it is there changes the way we see the universe. It reminds us that reality is often far more subtle than our instincts suggest. The sensations we experience, like the feeling that time is flowing past us, are useful tools for navigating life, but they are not perfect descriptions of the underlying structure of nature. When physics peels back those sensations and looks at the machinery underneath, it reveals a universe that is richer, stranger, and more fascinating than the simple stories our intuition first tells us. And perhaps that is the most important lesson of all. Understanding the universe is not about forcing reality to match our expectations. It is about expanding our imagination until it can match reality.